Moles. So just like converting. Sig fig question. So if you're just joining us, how it typically will start a GVL is just uh, is first couple minutes I just kind of let you guys type in any questions you have, and then we start going through it. Mole conversion. Half-life. All right, pretty good list. And if you have more questions, feel free to keep typing them in, and then I will talk about stuff. All right. So first thing we'll go over, what's going to be on it? Mole conversions. Let's go. Oh, this. All right, so mole conversions, we've learned that pretty much everything has to go through the mole. And how should I do this? Let's move it. No undo. I heard boys water polo lost, so heard it was a close game though. So mole, and then let's say I go on top. Let's say we go from here's atoms. So we don't win or lose. Yeah, you can still win or lose. It's like that. So let's say you're going from atoms to moles to grams, and pretty much what this is, it's dimensional analysis, just going from grams, moles, and atoms. Anytime you go between atoms and moles, you're going to be, so if you go this way, um, it'll be like you have some number of atoms and you want to get rid of atoms. So algebra, things on top, things on bottom, they'll cancel out. And you have to stop by the mole. The mole will get a 1 just because you're dealing with, for every 1 mole, that's how many particles there are. So that's why it's pretty much the same. It's like saying 1 dozen is 12 particles, 12 things. So if you have 1 dozen atoms, then you have 12 atoms, like that. Then down here, it'll always be 6.022 times 10 to the 23rd. Then if you want to go from moles to grams, you put 1 mole down here and then grams right here. And then this would be the molar mass of that element or that compound. And then if you were going from, I guess I'll just rewrite it here. If you're going from grams to moles to atoms, you would start off with some number of grams, and then you get rid of grams by putting it on the bottom. You have to stop by the mole. For every 1 mole, you have to use the molar mass of that element. So like for sodium, it's 22.99. Iron is 55.85, copper 63.55, things like that. Then once you're in moles, moles will be down there, and atoms will be up here. For every 1 mole, there's always 6.022 times 10 to the 23rd atom. If you're dealing with grandma, you always need molar mass. Yeah. So anytime you're going between grams and moles, moles and grams, you'll always be using molar mass. Anytime you're going from atoms to moles or moles to atoms, you'll be using the 6.022. So with this, we could just do some practice problems. Let's give you a few. Let's start off easier, then progress our way up. So try these out. We might not get too many students from other teachers because I forgot to send out an email to the other teachers about this. Oops. Hello. How was your limo ride? That was good, thanks. Nice. Oof, you're late. Focus on doing the problem. Because Aiden probably has an answer. Nope. I guess I should also do the problem too. I'll beat you guys to it. Done. All three answers are there. Should I start going over it, or do you guys want some time to actually do this? 1 second. 1 Mississippi. All right. Más tiempo. ¿Dónde está tu acento? Couple of minutes. Is this the gum chewing Kyle? Welcome. You can chew as much gum as you want here. Gum is disgusting. Crucial, do the problem. Stop typing. Wrong. No, you cannot. Only here. Just kidding. Haika. These are talking too much. Wait, why can't I hear the dings? Oh, there you go. Chat sounds. I should just start breaking up the poll into my periods to see which period I could get most of you guys to come to. Oh. Who's still working on it? Anyone? Should I start going over it? All right, so this first one, we're going from moles or grams to moles. And anytime you do this, first thing I always just do is just write down the number that is given to me. So I'll write, all right, I have 6.54 grams of carbon. Then I read the question and say, all right, how many moles? That's what I'm going to be going from grams to mole. So in this case, I need to get rid of grams. So grams are going to go on the bottom. And a mole is going to go on top because they live right next to each other. Sometimes what students will do is like on the top of their test or something, they'll just quickly jot down like, oh, gram, I guess if I do it like on the, oops, atoms, mole, grams. And then they'll write, oh, I could use 6.022 times 10 to the 23rd here, and then the molar mass here. So some students, I'll see this written on the top of their test, just so that they know, okay, anytime I'm going from grams to moles, I'm going to be using molar mass. If I go from moles to atoms, I'll be using the 6.022 times 10 to the 23rd. So that's a good idea, just so that you don't like skip a step or do anything weird about that. So going back to the problem now, so we have 6.54 grams of carbon, and we want to get rid of grams and go to moles. So Mr. Mole's favorite number is 1. So for every 1 mole, how many grams of carbon on there? So that's when you have to go to the periodic table and find the molar mass of it. So that's going to be 12.01. And then the grams of carbon cancel out, leaving you with 6.54 divided by 12.01, which is going to be 0.54454. 54454 dot dot dot. And then it just keeps going on and on and on. Then you go back and check sig figs. You're like, all right, 6.54 is the only number I used. So then I need 3 sig figs. So 0.545 moles of carbon. So that's your answer. We just make it simpler because, yeah, as long as you go to at least 2 past the decimal, your numbers will be pretty accurate. If you do more, obviously it'll be more accurate, but most of the time, by going 2 past the decimal, your numbers will still be the same, even if you went 100 past the decimal. So it's just a way to save work. Same reason why we're not using the entire Avogadro's number. We're just using 6.022 because we could have made you use like 6.022 and all the other numbers. You end up getting pretty much the same number. So for the second problem, we're going from molecules to moles. But here's the thing, I didn't write anything about molecules. Why do I have to use this word molecule? Why can't I just say atom? No, you won't have to, just the 6.022. Yeah, because it's a compound. It's made up of multiple elements. So you just can't say copper chloride atom. You have to say it's a molecule. So, but the work is exactly the same. It's just that we just change the word from atom to molecule. Same, same. So we have 7 point, is that a 5? I think so. 7.53 times 10 to the 24th molecule. So we abbreviate molecules. Whoa. Hold on. Drop my pen. So 7.53 times 10 to the 24th molecules of copper 2 chloride. Copper 2 chloride. And then we want to get rid of that. So molecules are going to go on the bottom of copper 2 chloride. And so if you look at the little thing that I drew, we're going from here to moles. So we have to stop by moles. So it'll be moles of copper 2 chloride. Then for every 1 mole of copper 2 chloride, there's going to be, if you check the top part, you have to use this number somewhere. 10 to the 23rd. So then if you divide these two numbers, you get 12.50415 dot dot dot. Then if you check the beginning number, you need 3 sig figs. So my answer is going to be 12.5 moles of copper 2 chloride. So then the last thing, another problem I could give you is now going through the entire conversion train, going from, let's say, grams all the way to atoms. So we're starting with 6.54 grams. So I specifically chose this number for a reason, because the very first problem used that same number. And the reason why when I do dimensional analysis, I do it in those boxes, is because, hey, technically we already did this problem right here. And if I just want to tack on one more step, I could just tack on a step. So I want to get rid of grams of carbon and go to moles of carbon. So 12.01 grams of carbon cancel out. Then I have to get rid of moles of carbon so that I could go to atoms of carbon. So for every 1 mole of carbon, there's 6.022 times 10 to the 23rd. And that eventually gets you 3.279 dot 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 times 10 to the 23rd. And with correct number sig figs, you need 3. So my answer is 3.28 times 10 to the 23rd atoms carbon. Nice. Easy stuff. All right, so that's like mole conversion. So really what you should remember is this stuff, just so that you're like, all right, anytime you have to go between atoms and moles, right here, you have to always use the 6.022 number somewhere, somehow. And then anytime you go between the moles and the grams, you have to always use the molar mass for that. So those are the things that you have to use. All right, so 0 to 20 minutes, we talked about mole conversions. Should I give you guys one more problem, or do you guys want to move on? Yes, yes, no. Go next. Let's do one more problem, just because Ryan said no. Anything else on the test that's not listed? Can you give us a house tour at the end? No. Alright. Ready, set, go. Right, he's not. Alright, is anyone here my first period? I had to see if I forgot to pass out anything. Anyone here my first period? Did they pass out the study guide with all the list of stuff? Alright, cool. So I think I had too much extra by the end of the day. Second period. Is anyone here from second period? Did I pass out the study guide stuff? Alright, cool. Crucials in third. Did I pass out the stuff for third period? You didn't get the study guide. Are you lying to me? Alright. You're unreliable. Who else is in my third period? Fourth period got it. Thanks, Alec. And I know sixth period got it. Then definitely third period didn't get it then. Stop typing. Do the problem. Alright. Whoever's in third period, remind me to give you that tomorrow. Or else I'll probably forget. Alright, who has this problem done? $1.0480 times times 10 to the 22nd. Same as Aiden. All of you guys got half off because none of you guys put units. Alright, so let's go over this. So we're going from grams to moles to atoms. At this point, we have to use molar mass. So we just put 1 mole. And at this point, we have to use the 6.022 times 10 to the 23rd. So let's start. We start with 0.0040010. So I specifically chose this number just so that you would see how many sig figs we need. So sodium, very long problem. So at this point, we want to get rid of grams. So grams are going to go down here of sodium. Then we have to stop by 1 mole of sodium. Then for every 1 mole of sodium, there's 22.99 grams of sodium. Grams of sodium cancel out. Now we're at mole town or mole's house. We want to get rid of moles, so we have to use 1 mole of sodium again. Then we have to use the 6.022 number. Third atoms of sodium. The moles of sodium will cancel out, leaving you with 0.004001 x, and you get a grand total of, how did you guys get that number? Oh, don't know how I got that number. I'm curious to see how multiple people got 2.4. Don't know. And then with sig figs, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5 times 10 to the 20th atoms of sodium. Right. It's because we forgot to divide by 22.99 grams. Oh, got it. Same. Nice. So that's the longest problem we could really give you for like going from grams to moles to atoms, or the opposite way. But good. Let's do one more because students tend to mess up the other way more, I think. Ready, set, go! All right, let's check. 1.005 times 10 to the 23rd atoms of calcium. So for this one, we're going from atoms to mole, or to 1 mole to grams. This point, you have to use 6.022 times 10 to the 23rd. And at this point, you have to use molar mass somehow. So first thing we need to get rid of is atoms of calcium. So I'm going to get rid of atoms, calcium down here, and then we have to stop by 1 mole of calcium. For every 1 mole of calcium, there's 6.022 times 10 to the 23rd atoms of calcium, and the atoms of calcium will cancel out, leaving you with moles. You have to get rid of that, and molar mass of calcium is 40.08 grams of calcium. Moles of calcium cancel out, and then what some people would have gotten, I was hoping someone would make this mistake, but I don't think anyone did, so that's good. So this is a common mistake that people make. 6.6888 times 10 to the 46. 1, 2, 3, 4, 6.689 times 10 to the 46 grams of calcium. So if you notice, the number is correct, but typically anytime you see something that's like times 10 to the 46 or like in the 40s, you probably did something wrong. Can anyone tell us what went wrong here? for anyone happen to know what went wrong? Yeah, the times 10 to the 23rd was multiplied instead of divided. So that's just a common mistake where people don't put enough parentheses around their numbers. Yeah. So it's actually not to the 46th, but sounds like you guys are right. Yep. So let's just get rid of that. Good. 6.689 grams of calcium. If you were off by a factor of 10, meaning you might have gotten something like 0.6689 grams of calcium. So I've been teaching a while, so I see some common mistakes that some students will make. This part is when you put it in your calculator like this. So some people will type it in something like this. I'm using a different calculator. But what they do is they do the 6.022 times 10 e23rd. This will always get you 10 off. Just because remember that e on the calculator. So if you do 6.022 times 10e23, what this actually corresponds to is 6.022 times 10 times 10 to the 23rd. Meaning this is actually 6.022 times 10 to the 24th, which is bad. So remember, when you do the 6.022, you don't need anything else because that E represents times 10 to the, and then the number you put after that is the exponent. Yeah, good. I just see some students make that mistake where they do the times 10 e to the 23rd. You don't need this extra 10 right there. All right, so that's mole conversions that you guys seem to be good with. Let's actually, Ryan, I'm just gonna kick you out then. Some of your stuff that you're saying, come on. 34 to something minutes. Mass defect. I don't know the mass of stuff. So mass defect, you're going to need to know the mass of certain things, like so let's say you wanted to calculate calculate and explain the mass defect of the element of carbon. So do this. Oh shoot. Let's see. No, so I have no clue what mass defect or half-lives are. Wow, go over mass defects. Mass change to energy by sustaining said atom. Not really. One question, should you call them mass amount atomic mass or atomic weight? Atomic mass. Mass is not weight. It is weight. Will the mass of protons, neutrons, electrons be provided? Yeah. So I'll give you that stuff, which I just had to look up because I don't even know them. Proton is 1.007276. Six atomic mass units. Neutron is 8664. 5 0 0 6 6 5 AMU. And then electrons are like 0.305486. So remember, you don't have to memorize these numbers, but you should know how to use them. What's the difference between those two and the molar mass? Atomic mass, atomic weight. Atomic mass and weight are typically thrown around interchangeably. And then molar mass, similar thing, it's just per mole of a substance. So that you can find the mass defect. So find the mass defect. Oh shoot, I don't even know the actual mass. Good old Google time. Actual mass. Let's hope this works. I don't know. And then given in nature it is so when given a mass defect problem, what you're trying to do is figure out that missing mass. So I'm just pulling these numbers, so I hope they work out. So if it's carbon 13, how many protons do we have? Good. We have 6 protons. How many neutrons for carbon 13? 7, and electrons are 6. Good. So then what you're trying to do is, okay, if you just got a carbon 13 atom in nature, it says it's this, 13.003355. So then let's check. If you got a carbon, it should weigh the same thing as its protons, neutrons, and electrons, because that's all that is. So this would be times 1.007276 times 1.008665 and times 0.000548. Nice. Annabelle already has an answer. You get 6.043656. You get 7.060655, and then you get 0.0032916. So this is all the things that make up the carbon 13. So if you add these all up, you get 13.10760026. So, all right, this is how much a carbon atom should weigh, carbon 13 atom. But if you caught one in the wild and you weighed it, it would only weigh 13.003355. So you subtract the actual, so minus 13.003355. What is that energy used for? 13.003355. And then just like Annabelle said we get 0.1042476. But with the correct number of sig figs, 1, 2, 3, 4, 5, 6 passed. 1.1248 AMU. Nice, Annabelle. Aiden, I don't know where you got that number. Jay, 7 AMU, too far off. Who else? Keeping the nucleus together, good. Not sustaining the atom. I just realized what I did wrong. What you do wrong? Actually, don't know what you did wrong. Oh, you did. Actually, I don't know. So this is the mass defect. So we would say, hey, this is the mass defect. And then what Kushal said, the sig figs is going to be based off this number right there. So 6 past the decimal. The mass defect, you would say, like Kushal said, hey, this is the mass that got converted to energy to keep the nucleus together. So good. You guys want another one of these? All right, that means I have to Google another thing. No, this is horrible. Well, if it's horrible now, it's better that it's horrible now and not horrible come test times. Atomic mass of what's the isotope? Nitrogen 15. Is there such thing? Oh yeah. Let's do 14. So it's this. All right, so I'm just going to erase all of this stuff. I don't even know what you guys are talking about half the time. I just ignore you guys. So just so that I don't have to retype all the mass of the proton and all that stuff, let's delete all this. Hopefully none of you needed this because now it's all gone. Get rid of all this. Get rid of all that. So calculate the mass defect of nitrogen 14 given the mass in nature is ready, set, go. Oops, can't read that, huh? Can you guys read that? Is that better? Or worse? No one wants to type because they're actually doing the problem, except Brian, who's currently typing. I don't know. You actually don't need the nitrogen part at the end because it's just AMU. Look at that, everyone. Dean's here. Ooh, different answers and different by just 10, factor of 10. Anyone else want to confirm? Same as Annabelle. Ooh, Aiden changed his answer. 11512. Nice. 4.09. It seems off. All right, let's talk about it. How many protons does nitrogen-14 have? 7. How many neutrons? 7. How many electrons? Oh, this was a terrible element to do because all the answers are 7. So then, to find the total mass of each thing, we want to know the protons, neutrons, and electrons. So this is just 1.007276. Whoa, what's going on? What? 1.007276, 1.008665 times 0.000548. And for me, on this calculator, I actually stored all those values. So I just have to do like 7A, 7B, 7C. B, 7C. Then we got 7.0509327, 7.060655, 0.0038402. What's great about storing values, because at this point now what I could do is this. 7A plus 7B plus 7C, then I press enter, we get 14.115472. So let's add these all up. 14.115472. Hopefully these numbers are the same as yours. Then we subtract it by the mass that's found in nature. 14.00031. And then we get a mass defect of 0.1151172, but with correct sig figs, 1, 2, 3, 5 passed. 0.11512 AMU. And then you should be able to explain what this is. So you would say something along the lines, this is the mass that got converted into energy to hold the nucleus together. So, good. So that's mass defects. 15 minutes we talked about. Mass defects. Next, half-lives. Half-life problems. I have to think of half-life problems. Half-life problems, the usual ones that you'll see is just figuring out how much is left. For half-life problems, these are essentially your 4 variables. Total time you have to wait, half-life time, starting amount, and then end amount. So these are the 4 variables for any given half-life problem. And from the problem, it should always give you 3 things. So you should always be able to start off with 3 things and you're just solving for that one. Typically, I suggest to students that they should figure out the number of half-lives first. And they do that by doing your total time divided by your half-life time. Because this number will give you number of times you have to divide by 2. Because remember, half-life, all you're doing is dividing by 2. So there's sig figs in half-life. Sig figs forever, Kushal. Sig figs forever. I might start calling you Zeus. But yeah, so let's do a problem. I'll try to give you a problem where it's each of the different types of half-life problems that you might see. You should say soy Zeus. All right. So this is a pretty standard half-life problem. El papel de Zeus fue en la basura, pobrecito. Let's try this. Do you teach AP Chem? Nope. Ready, set, go. Looks like you're not taking AP Chem. Nope. I stick with the college prep sciences. Get your work done, people. You guys should be done with this half-life problem by now. Cats? 54.6 cats? Ooh, looks like Alec beat you, Ryan. What's the starting amount? 873.6. All right, let's go through this. So total time was 513.2 years. Half-life time is, oh, whoops. That's down here. Total time is 2,502 or 52.8 years. Half-life time is 513 years. My start amount was 873.6 grams. So my final is, I don't know. So now out of these four things, you're only missing the final amount. So this is a pretty standard half-life problem. First thing I want to do is figure out the number of half-lives. And you do that by your total time divided by your half-life time. That's going to be 2052.8 divided by 513.2. And since I made up this number, how many half-lives will it take? 4 half-lives. So that means you'll be dividing by 2 4 times. So the arrow method where you just explicitly show each half-life. So there's 873.6. Then after each half-life, you're going down by half. So after one half-life, 873.6 divided by 2, you get 436.8. After another half-life, you get 218.4. After another half-life, you get 109.2. Then the last half-life, I can't fit it, so I'm going down, is 54.6. Nice. Only Annabelle and Christopher got the actual answer. Because you started off with 4 sig figs, you also want 4 sig figs. Is there a faster way to do that? Yes, the faster way involves a formula. Formula is your final amount equals your initial times 0.5 to the n, where n is that number of half-lives. So for this one, if you did that same exact stuff, your initial was 873.6 times 0.5 to the 4th power, because we figured out there was 4 half-lives. And then you get the same answer. You get 554.6, but you need 0. How do you do 0.5 to n on calculator? Because I can't find anything. So that one, I think you have to use the little hat. So like, I don't know, but on your calculator, see it, Ryan? But I think just that little caret, I think that's what math people call it. That little up sign. Sometimes people make a little smiley face. They're like, oh, so happy that we're doing chem. Things like that. Good luck on your draft. I heard Andrew Luck is a good QB to draft. All right, so this is a pretty standard half-life problem. So let's get you one that's a little less standard. Oh, that was too easy. Well, let's just still go with it. How much time has passed if there is 12.5% left of a radioactive substance and each half-life is 5 years? Ready, set, go. Dean, 15 bananas, cats, oranges, dogs, you're right. All right, so for this one, if you do the same 4 standards, do you guys even know who Dean is? No. Yeah, he's her friend. Total time is what we're looking for. Half-life time is 5 years. Start amount, it seems like I don't have a starting amount, and I have a final amount of 12.5%. Because, hey, if there's 12.5% left, keyword, so anytime you're given 2 of these things, and you're like, all right, Mr. Lee said they have to give me 3 of these variables, that means you should be able to figure out a 3rd variable really quick without doing any math. Anytime you're given a percent that there's 12.5% left of this thing, if you think about it, in the start, what percent do you always start with? Before you complete anything, before you eat anything, you always start off with 100%. So you could figure out that this is 100%. Then at this point, you still want to try to figure out the number of half-lives, but you can't do the total time divided by half-life time, because you don't know 2 of those things. So what you do now is you're like, all right, I have 100, and I eventually need to get to 12.5%, And what is the only thing we do in half-lives? The only math, pretty much, that we do. Yeah, we just split it in half, we divide by 2. So, all right, if I started with 100 and I went through one half-life, what percent would I have now? 50. So, like, all right, we're getting there. If I had another half-life, I'd be at 25%. So almost there. So then if I do one more half-life, then I'm finally at my 12.5%. It's like, hey, this is actually what I wanted to get to. And it only took me 1, 2, 3 half-lives. So now you know that how many half-lives are right here. So you have 3 equals the total time you waited. And how long was each half-life? 5 years. Then you could just solve for the total time, and then that ends up being 15 years. Nice. Easy stuff? No? Yeah. We'll see. We'll see how hard of a problem I can make for your test. All right. That's Half-Life. Oh, nice. Now you got a leg up when you actually do learn Half-Life stuff. 15 minutes to an hour and 4 minutes. Talk about Half-Life. So last thing we're going to talk about, we'll go through density. Yeah. Density we actually covered in our previous GVL. So if you want extra practice with that, going more in depth, more practice, feel free to watch that one. But since someone asked about density, we'll talk about it. Yep. Definitely sounds like I did not give period 3 that study guide thing. It's because you guys talk too much third period. I always have to take my time to tell you guys to stop talking. That's why. Maybe I'll just happen to forget to give you guys the study guide again. Just kidding. Wow. Now blaming on the period? Yeah. It's all third period's fault. Not my fault. All right. Density. So density equals, and everybody loves math, so you just draw a big old heart. You're like, woohoo, we love density. But then you kill the heart because no one loves math. And if you look, it kind of looks like a M on top and a V on the bottom. So that's how most people, or not most people, that's how I typically remember density is mass over volume. I personally don't like to show you the little pyramid method. It'll work anytime there's 3 variables that are directly, yeah, just 3 variables. But anytime there's more variables than that, the pyramid method won't really work. I guess I'll still show it to you, but after. So pretty much this is just algebra. On the tests, on the quiz, on any homework, similar to Half-Life, density, mass, volume. You'll for density problems, there's 3 variables, and you always have to be given at least 2 of them so you can solve for that last one. Isotopes and fission / So then this volume would be the one that you're like looking for. So this is just algebra. I guess we could do some density problems. Let's see, calculate the density of ready, set, go. Yes, you must remember CPCTC. Congruent parts of congruent triangles are congruent. Is is that even their mascot? I just assumed. It looks like a horse. I went with Bronco. QED, ASA, side, 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 stuff like that. Vertical angles. I know everything. Just kidding. Who has the answer? Oh man, is that the actual answer? I just literally just put my finger on the numbers and I just went back and forth. All right, so remember, density is a heart. Let's kill the heart. It says mass over volume. The mass is 654.43 kilograms. Actually, none of you guys got the right answer. Oh wait, Aiden might have. I know I'm supposed to have five, but the calculator doesn't give us the numbers. Oh, interesting. 1, 2, 3, 4, 5, 6, 7, 6, 5, 4, 3. Such a ridiculous number. 654.43, but good job, Aiden, for explaining that you should have 5 sig figs, but the calculator doesn't allow you to. But Annabelle found the workaround where she probably put her calculator in scientific notation form, but her units are wrong. 654.43 divided by 1, 2, 3, 4, 5, 6, 7, 6, 5, 4, 3. Answer is 5.31288 times 10 to the negative 8th. And with the correct number of sig figs, that's supposed to be a 3. It'd be 5.3009 times 10 to the negative 8th kilograms per milliliter. For those of you with calculators that didn't go all the way, yeah. Good, so that's like a very easy density problem where you're just dividing those two numbers, then you're set. Let's do another density problem where it's a little different. Who else can I talk about? Ooh, density of can we have quadratic numbers as angles, Mr. Lee? Quadratic numbers as angles. Angles could be any numbers. What do you mean quadratic numbers? The density of the water at the water pool in Matsell's lost today is 1.03 grams per milliliter. What volume of water was there if the mass of the pool was 5,628.03? I don't know. I don't know what you're talking about, but I'm going to say yes. Correct, Kaylee. Good point. No, wait. What volume of water mass is fine? No, that's fine. Oh, that's your answer. Oh, that was quick. Let's go over it. I thought you were correcting me. Which I was like, oh yeah, maybe I'm wrong. They only lost by 1. But a loss is a loss, right, Shanna? Right. M over V. We know the density is 1.03. We know the mass is 5,628.03 over V. Then at this point, if you got this answer, if you got 1.830 dot 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 times 10 to the negative fourth, that's what some people get. You should have said the density guy who cut me off. This is 1 over v. So you just have to flip it, and then you end up actually getting 5464.1 dot dot dot, and you need 3 sig figs, so it's 5460 milliliters of water. So I always suggest anytime we have variables on the bottom, just cross multiply so no variables are on the bottom. So if you cross multiply, it would be 1.03 V equals 5628.03. Then you divide both sides by 1.03. So V equals 5464.106 dot dot dot. But with correct number sig figs, 5460. This tablet milliliters. Good. Adios. It's good. So that's density stuff. So it's just algebra. If you want more practice, watch the other GVL. We probably went a little bit more in depth for that one. Isotopes. What about isotopes? Yeah, there's actually a lot of good resources that you can watch on YouTube. If you never understand stuff, that's where I learned some things. Oh, like finding the average atomic mass. I think that's what you're talking about. I'm assuming. Yeah, all right, so we'll do one of those. So that's like finding average atomic mass, and this I can't really just come up with a problem in my head. Let's do this one. So this was also from today's assignment. Let's say 53.25 of element blah blah blah. 54.25 of blah 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 blah. Let's make it 100 so things the actual element. And then 155, 25, blah 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 blah. This one is 25.01%. This is 30.19%. And I'm using random percent, so 9, you get 40. Figure out the average atomic mass of this element of blah 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 blah. Ready, set, go. That usually is the case with most people. Just like bio and chem, if you're good at bio, then chem's a little bit different. But people who are good at algebra tend to struggle with geometry. Well, we'll see if you're good at chem, then maybe bio will be a struggle. Maybe you're just good at everything. Then we might as well call you Mr. Lee then. Haha. Wrong. You're wrong. Do this problem. I should really move that lamp eventually. Or every time I move my head, it gets really bright. Dark, wherever it's the dark shadow. I'm like if you don't put your profile picture in something, which is a dark profile. Dang, you guys are still here after an hour 17. So remember, with this, you're multiplying the percent abundance with the mass number. Does anyone have an answer, or are you still working on it? Working. The new iPhone 11 came out. Can't really work right now since eating pizza. Pizza. Legit? Yes, you could Google iPhone 11. It came out. I think an XR is gonna last me 5 years. To what sig figs? Typically with this stuff, when base your sig figs on the percent, unless your teacher tells you otherwise. Sometimes your teacher will say, just round to the hundredth, two past the decimal. But this one, let's just say, just so that you're practicing sig figs, let's go with just base it off the percent. So let's go through this problem. First thing I like to do is change the percent to a decimal. So it'll be 0.2501. This becomes 0.3019. This becomes 0.4480. Oh, I thought that was real. Then we're not multiplying by the atomic number. We're multiplying by the mass number. Times 153 times 154 times 155. So we do that, 0.2501 times 153, you get 38.2653. 3019 times 154, you get 46.4926, and then 0.448 times 155, 69.44. A lot of you guys, for some reason, like when you type the 0.4480 into your calculator, you guys actually type in 0.4480. Is there any point for this zero at the end? There's not. So I don't know why some of you guys put it. It's just afraid. All right. Emma doesn't put it in though. She knows. 38.2653. And then we're adding up all these numbers. 38.2653 plus 46.4926 plus 69.44. And we get a normal person answer of 154.1979. But now, sig figs, everyone's favorite thing. This had 4 sig figs, so this needs 4 sig figs. So 1, 2, 3, 4. 4 sig figs, so 1, 2, 3, 4. 4 sig figs, so 1, 2, 3, 4. Then when we add them, remember, we have different set of rules for adding and subtracting. Ooh, Dean, you shouldn't have changed your answer. Because now that we're adding, this one is 2 past the decimal, this one is 2 past the decimal, and this one's also 2 past the decimal. So my answer actually has to be 2 past the decimal. So if you think about it, you're like, all right, I have to check to see if I have to round. Am I going to round this 9 up or keep it a 9? Yeah, you're going to round up, which means the 19 becomes a 20, but you have to keep that 0 in there. So their answer is 154.2. Remember, my answers are 2 past the decimal, 2 past the decimal, 2 past the decimal. So my answer has to be 2 past the decimal. First answer was right, Dean. So AMU. Like that. Yeah, follow your gut. Senor Lee, atomic weight versus mass. for your answer. Exponential. They're used interchangeably. Atomic weight versus atomic mass. I think mass is more accurate. But that I actually don't know. Let's ask Google. Atomic mass versus atomic weight. Because weight is inherently with gravity. Weighted average. Oh, okay. I guess if you want to be more accurate, atomic weight is the average weight of all the isotopes, and atomic mass is like mass number from just a reputable source. You always have to check your sources. Yeah, so atomic mass is like protons and neutrons, and then the weight is adding them all up and averaging them. But that also depends on gravity and stuff. And atomic number is protons. All right, so last thing we're going to talk about, I guess we talked about isotopes. Let's go average atomic weight. Fission and fusion. Fission, fusion. We just talked about what they were. Fission is where heavy nucleus breaks up into lighter nuclei plus some energy. So that's all that is. If you think about fission, if you think about like the San Andreas Fault, it's a fissure in the ground. And one type of fissure, what happens is the crack gets bigger and bigger and bigger and bigger because the plates are spreading apart from each other. So that's fission. Yeah. And this is the one in the nuclear reactors or atomic bomb, all that. Whereas fusion, this is like if you ever heard of fusion food, you're putting two cultures' foods together to create a fusion. This is where light weight nuclei, they like ram into each other, they combine together to make a heavyweight nucleus plus some energy. This is the one that occurs in stars and stuff. So if you think about fusion, you can think about like fusion food, and then you rate them on Yelp using stars. Look at that. I just made that up right now. But that's just really the thing you have to know about fission and fusion. 1 star equals bad food place, or it's just really authentic. All right. With that, we've completed an hour and almost a half of review. Look at that. You guys are all ready for the test. Yeah, I'll do that. Yeah, the test is tomorrow. For nuclear chem, things like that. So the main thing about nuclear chem is the top numbers have to equal the reactants and product side. So if I do a quick thing, I don't know actual stuff, so I'm just gonna make stuff up. Let's see. There's 218. Alpha decay. So you might get something like this. where unstable lead atom is going to break apart. It's going to go through alpha decay. Alpha decay because you're getting rid of a helium. So what's going to be left? This stuff, it's really not that bad. You just have to remember that the top number on the reactant side, 218, has to equal the top numbers on the product side. So 4 plus something in this case. So we'll call that x. So then if you subtract 4 from both sides, x is going to be 214. Then, if I use a different color, the bottom number on the reactant side, so 82, has to equal the bottom numbers on the product side. So it'll be 2 plus x in this case right there. That means x in this case would be 80. Then if you look on the periodic table to figure out which element it is, 80 is wait, right there. It's mercury. So you put Hg right there. So really all you're doing is making sure the top numbers stay the same, bottom numbers stay the same. Why? Why can't the numbers be different? Exactly. Law of conservation of mass, meaning if you started off with 82 protons, by the end of it, you should have 82 protons. Same thing, protons and neutrons, 218. That means on the product side, you should have some combination of 218 protons and neutrons. And Annabelle, if you want more practice and stuff, don't worry. Tomorrow and Thursday, we'll just be practicing a bunch of stuff. So yeah. So now we're officially done. I'm hungry. Nuclear chem. And if you want more stuff, I don't know. I don't remember what we did last year or the year before that. You could check YouTube real quick, and then you could see whether or not we did more nuclear chem stuff, so you could have a little bit more review there. But yeah, thanks for coming. You guys definitely made it entertaining. So I'll stop the meeting and then stop the recording.